Today we're going to talk about type 5 equilibrium concentrations and our calculations, And we sort of saw a little bit of this with type 4 when we were doing the perfect squares. So in this particular scenario, again, you are given an equilibrium reaction, meaning the forward rate proceeds at the same rate as the reverse reaction. And they give you a certain amount of each of your reactants to start off with. So I'm just going to make this, instead of 2, it's 2.0 moles of hydrogen, 3.0 moles of iodine are placed in a 1.0 liter vessel. So we have 2 sig fig. And remember that mole does not mean concentration. So you have to use this calculation, moles divided by volume in liters, in order to figure out what your concentration is. This happens to be a 1 liter vessel, so this is easy conversion. So we have 2 moles per liter of hydrogen. We have 3 moles per liter of iodine. And again, unless specified otherwise, you assume that you have 0 concentration of products initially, right? Until these collide to make some of the product. They also tell us our KEQ value is 25. And remember, what that indicates is this value is a lot greater than 1. So we should have more product at equilibrium than we do reactant, okay, when this system comes to equilibrium. So these are your initial concentrations. They do not give us any equilibrium concentration of any other item. So what you must do in this case is let your change column equal to your mole ratio column, and we allocate X values in that column. So we see that this is a 1:1:2 ratio. We know that reactants get used up over time. So this will be a minus X. This will be a minus X. And because of this too, we would say that the concentration increases by 2 times that amount over a given period of time. Your equilibrium column is equal to your initial and your change column added together. So here we have 2.0 minus X, 3.0 minus X, and 2X. So when we set up our mass action expression moving forward, remember that it's always products over reactants raised to their exponent. So we have KEQ equals the concentration of HI, all divided by the concentration of H2 times I2. And we want to just double check. We want to make sure that in the top that is squared because of that 2. And we take a look here. Then what we do is we substitute in. So here we have a 25. This is a 2x on the top squared all over 2.0 minus x times 3.0 minus x. Okay, and what do we do with that moving forward? Well, what we have to do is we have to employ the distributive property. So we must expand what's on the bottom and apply this squared to what's on top. So on the top, don't forget, not only are you squaring the x value, you're also squaring the numerical value. So we have 4x squared on the top. And on the bottom, when I use the distributive property, I get 6 minus 5x plus x squared. And that's all set equal to 25. Then what I want to do is I want to take this and I move it up to the other side of the equal sign. So instead of being divided, it will be multiplied. So I'm going to take 25 times this 6 minus 5x plus x squared, and that's equal to 4x squared. Then what you want to do is you want to multiply everything that's in that bracket by 25, that's outside the bracket. So we end up getting 150 minus 125x plus 25x squared is equal to 4x squared. What we want to do is we want to get it into the form of the quadratic equation that is shown up above here, where we have ax squared plus bx plus c equals 0. So what I want to do is I want to sort of rearrange this to make it look like that. So when I bring this to the other side, we're going to subtract. And so I'm going to have 21x squared, right? And then I will have minus 125x plus 150, set that all equal to 0. Okay, so what we want to do at this point in time, we need to use the quadratic formula in order to solve for x. So what we're going to do is we're going to set x equal to negative b, which happens to be negative 125, plus or minus the square root of negative 125 squared minus 4 times 21 times 150, all divided by 2a, which is 2 times 21. Now, when I put that into my calculator and I do everything underneath the square root sign, what I end up with is positive 125 plus or minus 55, all divided by 42. Then we know that x is going to give you two different values. And in this case, I end up with x equals 4.3 or x equals 1.7. And again, I just kept two significant digits. So only one of these is correct. When I go back up and I take a look at my equilibrium row in the ICE table, I notice that 4.3 is not going to work because 2 minus 4.3 would give you a negative concentration. You cannot have a negative concentration. So this one will not work. So what I'm going to do is I'm going to go back up here and I'm going to just kind of maybe rewrite another row. So I will show what my equilibrium concentrations are now that I know that my x is equal to 1.7. So when I do that, I get 2 minus 1.7 gives me 0.30 moles per liter. Again, I'm keeping 2 sig fig. Remember, this 0 out front is just a placeholder. Then we get 1.3 moles per liter, and we get 3.4 moles per liter. So these are the equilibrium concentrations for this particular reaction. You could not use the perfect square method in this case because you did not have something squared on the top or the bottom. So when you run into a circumstance like that, you must use the quadratic formula in order to solve this type of question.